Good day and welcome to the Hydrology section's Walter B. Langbein Lecture. On behalf of my co-session chairs, Sankar Arumugam, our fall meeting program chair from the section, and Rich Vogel, chair of the Langbein Lecture Award Committee this year, we want to welcome you to this pre-recorded lecture and award ceremony. I'm sure none of us expected to be meeting remotely, and even so, to be trying out our acting skills in front of a camera this late in life. In that vein, I want to send a thank you and appreciations to all of the citationists and awardees you're going to hear from today, as well as on Thursday's Witherspoon Lecture, for your patience, your cooperation in preparing this video session. It has not been easy. Much of this was recorded almost a month ago. People were pretty stressed to get things done, and I really appreciate that the entire team worked together to make a great presentation. That team includes the AGU staff and the projection staff behind the scenes who worked long hours to make the entire meeting work. If you ever wondered how much work goes into putting together a 30-minute sitcom or a 60-minute documentary, I can tell you that it is a lot of work and a fair amount of stress. So I know I'm sticking with my day job. Today we'll begin our celebration with the union and section awardees. We'll present the Hydrologic section's Hydrologic Sciences Award, and the Langbein Lecture Award will follow that with a live question and answer. Raphael Bras and myself should be on the line after his lecture, and I'll be moderating the questions. So please type your questions into the question box. Unlike a normal lecture, you can ask your questions electronically at any time during the presentation. They won't disrupt the flow of the lecture. And I'll remind you of that when we get close. Due to time constraints, we also won't be awarding all of the section awards today. We'll be saving some of those for the Witherspoon Lecture on Thursday. So I encourage you to attend the Witherspoon Lecture. And just as a reminder, the Witherspoon Lecture is scheduled for the same time slot as we are today on Thursday. I'm very proud to say that the section's scientific rigor and accomplishments were extremely well recognized by the union this year. And our first award is the Robert E. Horton Medalist for 2020. The Horton Medal recognizes outstanding contributions to the field of hydrology over a lifetime. And it's my pleasure and honor to recognize longtime friend and colleague Martinus Rien van Gunukten as the 2020 Robert Horton Medalist. Congratulations, Rien. It's an honor well deserved. The union award ceremonies, as of this video, are scheduled for tomorrow, Wednesday at 6 p.m. Eastern Standard Time. And I do encourage you to attend those award ceremonies virtually, as you'll be able to recognize and see our colleagues. If anything changes on that time frame, I will let you know during the question and answer period that will be live. This year, the hydrology section was very visible on the awards and medals platform of this meeting, and it's my pleasure to recognize these outstanding colleagues here. The Union Ambassador Award is given to those who have reached out and contributed significantly to our community. The Union Ambassador Award also comes with designation of AGU Fellow. I'm proud to announce that the hydrology section had 2 Ambassador Awards this year, Kiva Madani from Yale University and Carletta Chief from the University of Arizona. Thanks for your service to science and society, and congratulations to both of you on this incredible honor. At the union level, we have several other medalists and awards from the section to recognize. Yoshihide Wada is the recipient of one of the McElwain medals this year. Congratulations, Yoshihide. Subimal Ghosh is recognized at the union level with the Devendra Lal Memorial Award. And Faisal Hossain is recognized at the union level with the International Award. Again, congratulations to all of you, and we're looking forward to seeing you tomorrow when you receive your awards. AGU awards 0.1% of its membership each year, designated as a Fellow of the AGU, recognizing outstanding contributions. This year, it's my pleasure to recognize our 7 hydrology section members who are primary in our section for receiving fellowship this year. Rainer Helmig, Shafiqul Islam, Aaron Packman, Laura Pyrak-Nolte, Remco Aulenhout, Andrew Western, and Gary Wilgoose. Congratulations. We're all looking forward to seeing you cross the stage virtually this year, and looking forward to shaking your hands when we can. And now for the section's awards. My pleasure to recognize our 3 Hydrologic Science Early Career Award winners this year. They are Simone Fatiche from the National University of Singapore, Veronica Morales from the University of California, Davis, and Niko Wanders from Utrecht University. We'll be formally recognizing them on Thursday at the Witherspoon Lecture, so please do attend to hear from them and their citationists. But you can also hear what they've been up to in their great science by going onto the Hydrology Section's AGU website and viewing their November Early Career Webinar Series lectures. They should be under the Lectures and Events tab, and this was something we instigated this year to give a little bit more opportunity to hear what our young scientists have been doing and what our field is going to be doing in the future. They were really stimulating seminars. We still have one left as of this recording. Niko Wanders is coming up in a few days, so please do try to take a look at those in your leisure. Congratulations. Our next award is the Hydrologic Sciences Award. Hydrologic Sciences Award was established in 1956 and is granted by our section for outstanding contributions in the field of hydrology with an emphasis on results in the last 5 years. It's my pleasure to award the Hydrologic Sciences Award to James J. Familietti from the University of Saskatchewan. I'm going to ask Dennis Lettenmeyer to come up and give the citation, and that will be followed by Jay's acceptance of the award. This year, Jay, unfortunately, we're going to have to send the award plaque by the post, so hopefully it will be able to get across the border. Dennis?
Thank you, Scott. I'm pleased to introduce this year's Hydrologic Science Awardee, James S. J. Familietti. I first met Jay when he was a graduate student working with Eric Wood at Princeton in the late 1980s. His dissertation work showed how land hydrologic processes, especially downslope redistribution of soil moisture, could affect large-scale moisture and energy fluxes, and challenged the then prevailing view that small-scale heterogeneities essentially averaged out in the estimation of, for instance, evapotranspiration. After joining the University of Texas faculty, he turned his attention to the then upcoming GRACE satellite mission and how it might be used by hydrologists. Because GRACE would measure the effects of all variations in moisture from the satellite to the center of the Earth, it would be a fundamentally new observation. However, many in hydrology, myself included, were skeptical that much would come of it given the very coarse spatial scales. Jay, with then student Matt Rodell, showed in pre-launch papers that even given the coarse spatial scales, new insights could result in the water balance of large river basins and groundwater storage variations, for instance. The launch of GRACE in 2002 led to an explosion of papers, many authored or co-authored by Jay and his colleagues. A 2007 Hydrogeology Journal paper introduced a method for isolating changes in groundwater storage from GRACE data and was subsequently used to quantify massive rates of depletion of groundwater in northern India in a 2009 Nature paper, which has now been cited almost 1,200 times. The technique has been replicated elsewhere by hundreds of studies. Papers by Jay's group in particular focused on California's Central Valley, the Middle East, and the Colorado River Basin. Other papers followed that used GRACE data to estimate continental runoff and even for predicting flood vulnerability. Beyond his research, Jay has assumed a leadership role in the hydrologic community through his involvement in professional organizations, including most prominently AGU. He served as the Hydrology Section Program Chair for the AGU Fall Meeting in 2004 and is a past editor-in-chief of Geophysical Research Letters. He's also served the profession in many other ways, too numerous to mention in this brief introduction. For all these reasons and others noted in the nomination and supporting letters, Larry Ban, Tycon Oki, and Krista Peters-Ledard, and I as nominator, heartily congratulate Jay.
It's a great honor to receive this year's Hydrologic Sciences Award. To be listed alongside the previous awardees is something that I never dreamed of. I'd like to thank my nominator, Dennis Lettenmeyer, Matt Rodell, my letter writers, and the awards committee members for my selection. When I enrolled at Tufts University as a freshman, I thought I wanted to be a veterinarian, but in my fourth semester I discovered geology, and that put me on a path towards hydrology and earth system science from which I've never wavered. My mentors along this path have had such a profound impact on my career that I'm forever indebted to them. Jim Hume, Sarush Sarushian, Eric Wood, Dave Schimmel, Jack Sharp, Clark Wilson, and Bill Rieberg all have had a steady hand in guiding me through the years. Of all the work that I've done in my career, I'm most proud of what we were able to accomplish with the NASA GRACE mission. That work started while I was at UT Austin, and I owe Clark, Byron Tapley, Steve Neeram, Don Chambers, and Mike Watkins a debt of gratitude for encouraging me to get involved, and to Matt for his trust in me as a supervisor. It really took off after I moved to UC Irvine, and it came to fruition during the height of the California drought in the early 2010s with my amazing team at the UC Center for Hydrologic Modeling. That work led to what has effectively become a second career in science communication and government advising, with the help and encouragement of Kathy Eiler, Congresswoman Grace Napolitano, and Dave Wegner, and that work continues to this day. The GRACE research, and in particular the regional and global groundwater work with Matt, Hassan Syed, Sasha Ritchie, J.T. Rager, Minhui Lo, Stephanie Castle, Kate Voss, and Brian Thomas, paints such a compelling picture of water insecurity and therefore food insecurity that it has driven me into the take action part of my career. I'm grateful for the opportunities to do just that from my post at the University of Saskatchewan. It's cold in Canada, but I'm ever so grateful for the warm embrace and friendship of my USask colleagues, Karen Chad, Jeff McDonald, John Pomeroy, Al Pietranero, and all of the wonderful staff at the Global Institute for Water Security. Family is like water. Without it, we could not exist. This award was made possible by my family's unlimited love, support, and encouragement. This award was also made possible by my other family, my research family, and it is shared with all of you. Thank you.
Congratulations, Jay. It is now my pleasure to recognize the 2020 Langbein Lecture Award, awarded to Professor Raphael Bras from Georgia Tech University. Langbein Lecture Award recognizes lifetime achievements of a senior scientist to the science of hydrology and unselfish cooperation in hydrologic research. It's my pleasure to bring to the stage Juan Valdez, who will be the citationist for the Langbein Lecture this year. We'll follow with the acceptance award from Raphael Bras, and then we'll roll directly into the Langbein Lecture. So I do encourage you, since you won't be seeing me for a little while, please do remember to put your questions in the question box as we're going through the lecture, and we'll do our best in the time we have at the conclusion of the lecture to answer those questions. Juan.
Thank you. It gives me great pleasure to introduce Professor Rafael Luis Bras, this year's recipient of the American Geophysical Union Langbein Lecture. Rafael has a vision of future fields and his contact with other areas in some surpass in our discipline. He has brought new action in hydrology, climatology, eco-hydrology, and stochastic process, among others. Select example of his accomplishments include the book Random Function Hydrology, co-authored with Rodriguez Iturbe, that provide a needed review and critical analysis of more than 30 years of stochastic hydrology and fill a much-needed space in the literature. The book provides a very clear explanation of random fields of precipitation and the application of these to hydrologic design. Despite its almost 40 years since publication, still is widely used in classroom and in research. Rafael also has significant contributions to the field of hydrogeomorphology, where in the words of one of the nominators, Professor Andrea Rinaldo, he brought quantitative hydrologic approaches deeply into the study of geologic and geomorphologic data. His work provided quantitative tools to extract objective patterns of river networks from digital elevation maps. In other venues of research, in a series of papers started with Tarboton et al., Rafael and his collaborators developed novel approaches to hydrometeorology and to the analysis of DEM using GIS tools to remove sinks and peaks, ensuring a proper delineation of watersheds, sub-basins, and streams, and avoid the generation of discontinuous drainage systems. Professor Fatih El-Tahir said in his nomination letter, Rafael's outstanding contributions to the study of rainfall extended beyond statistical approaches, since he later integrated hydrologic and meteorological approaches, resulting in the discovery of regularity and spatial patterns of rainfall cells at the mesoscale, and in defining the chaotic nature of rainfall dynamics based on observation and numerical model simulations. Using the principle of maximum entropy, Rafael and his collaborator Juan developed a model to represent surface heat fluxes at the energy balance. This provided a new view of the heat exchange at the land-atmosphere interface and greatly facilitated the development of new approaches to model energy balances. In his scientific career, Rafael also has unique ability and a caring attitude to teaching, having won teaching award at several academic institutions. He has been extremely active in all aspects of the science and education from primary to university students. He has served in leadership positions at MIT, University of California, Irvine, and Georgia Tech. Furthermore, Rafael has done outstanding service to the American Geophysical Union, both to the hydrology section, where he served as president, and to the union as a whole. In summary, Rafael has three outstanding characteristics that make him uniquely qualified for this award: outstanding integrity, a relentless search for understanding of the fundamental of physical processes, and a rare ability to relate his field to other fields of scientific knowledge. These characteristics have led him to explain and formulate areas of hydrology, morphology, and climatology, which have taken new direction after his exploration. Thank you.
After 45 years in the business, I have a lot of people to thank, because I certainly did not make it here by myself. In fact, I am proud to say that the list of friends and mentors is so large that I cannot name them all here. Let me begin with those that nominated me. Juan Valdez, who offered such a kind citation. Colleague and longtime dear friend, thank you. Darren Tecabe, whom I know since he first applied as a student and was a former colleague at MIT. El Fatih El Tahir, professor at MIT, former student, and dear friend. Thank you all. Over the years, many have provided opportunities and advice. Three stand out. The late Donald Harleman. I simply would not be here without him. He literally convinced me and got me into graduate school at MIT. And he was like a father to me until his death. Pete Eagleson, he taught me excellence and what hydrologic science is all about. Ignacio Rodriguez Iturbe, my doctoral advisor, whose energy and innovative thinking has opened many avenues of study in hydrology. He's a friend and brother. I have to thank the institutions I have worked in. At the Massachusetts Institute of Technology, the University of California, Irvine, and the Georgia Institute of Technology, I simply have worked with the very best. All three places not only tolerated, but supported the administrator that insisted on doing research. A few weeks ago, I stepped down as provost of Georgia Tech after 10 wonderful years of leading an extraordinary university. My Georgia Tech colleagues need special mention because they have lived a great adventure with me and because they have been extraordinarily kind. It is important that I acknowledge the American Geophysical Union. The union cemented my success when, as a young scientist and faculty member, I won the Hydrologic Sciences Award and the McElwain Medal. Those were watershed moments in my life. Hydrology has the best home possible at the American Geophysical Union. Last but not least, I want to thank my over 70 students and postdocs, my friends, that keep in touch from every corner of the world. They are my proudest achievement. In fact, I want to dedicate the Langbein Lecture to one of my dearest students, the late Professor Jorge Ramirez from Colorado State University. Thank you very, very much. Back in 1987, Pete Eagleson and I wrote an editorial in EOS entitled Hydrology, the Forgotten Earth Science. We argued that development of hydrology had been driven by societal problems at such a rate that, quote, the cultivation of hydrology as a science per se has not occurred, and there has been no established platform within the hierarchy of science on which to build a coherent understanding of the global water cycle. We also wrote, quote, "Progress in the science is currently data limited, yet we stand at the threshold of having undreamed of resolution of hydrologic quantities in both time and space, and perhaps even in real time," end quote. And we ended with a call to prepare a national plan for the development of the science. A lot has changed since 1987. Not one but two national plans have been published, and the explosion of data has occurred largely driven by advances in sensors and communications technology. Central to that explosion of data are the satellites that resulted from NASA's Earth Observing System program. The success of NASA in observing the Earth is truly an unheralded triumph of modern science and technology. But the progress in hydrologic sciences would not have been possible without the American Geophysical Union, Walter Langbein, and the United States Geological Survey that housed many of the pioneers in hydrologic sciences. That narrative of the beginnings of hydrologic science is well developed by another giant in the field, James Jim Doug, in the 1996 paper Walter Langbein and the Emergence of Scientific Hydrology, recommended reading for all. The Transactions of the American Geophysical Union, the first and only union journal then, was the main outlet for hydrologists. Names like Horton, Tice, Sherman, Sharp, Holtan, Schum, and Langbein appear regularly in the journal pages. Langbein was a versatile hydrologist. He was comfortable with all the tools of the trade at the time. Generally, his approach combined the use of extensive data and a large dose of analysis to interpret the data and yield generalizable results. For the times, the records he commonly used were extraordinarily large, sometimes involving observations, for example, of parameters of hydraulic geometry in hundreds of river basins. As Doug in 1996 points out, the last phase of Langbein's life focused on the problem of, quote, usefulness of extensive programs for the collection of basic data depends on correct and timely interpretation of the data. The matter appears to be one of emphasis. An equally eloquent plea can be made for more analysis of principles and for more sensitive data. A basic data program can go wrong when there's an imbalance on either side, end of quote. The reality now, as I stated before, is that the cost per unit data and the time and space coverage of key hydrologic variables over the Earth has gone down to the point that Langbein's balance has shifted. Until late 20th century, hydrology and many other earth sciences developed in a limited data environment. For the most part, researchers and practitioners avail themselves of data of very low resolution in time and space. In hydrology, that meant point observations of fluxes like precipitation and evaporation, and of state variables like soil moisture, temperature, and topography. Those observations were rarely hourly, sometimes daily, and more commonly weekly and monthly. That situation forced hydrologists to rely on significant data extrapolation and on conceptual mathematical models designed to capture the broad system behavior. For the longest time, hydrologists only had, at best, a measurement of discharge at an outlet and one, maybe a few, point measurements of rainfall over a basin. Facing this reality, Sherman, in the 1930s, introduced the concept of the unit hydrograph. The assumption is that the basin is a linear system characterized by a response function to a unit input of effective rainfall of a unit duration. This idea was further generalized by Duke in his master's thesis and by many others following. The generalization shown on the left corner diagram is based on taking the limit of the input duration to 0, resulting on the response to an instantaneous unit input or the instantaneous unit hydrograph. The idea of a characterizing function is powerful. Theoretically, the response to all inputs can then be obtained by a simple convolution as indicated in the diagram. In system theory, this is called a black box model. In hydrology, we call it a linear reservoir. The embellishment of this concept fueled hydrology for many years, even to this day. Parameterizations of the instantaneous unit hydrograph in terms of basin characteristics like geomorphology and climate abound. They all try to overcome a dearth of data, even to estimate a simple response function. Linear reservoirs were connected in a series and parallel constructs to add flexibility to the basin representation, particularly large basins. The advent of computers in the late 50s and 60s inspired many to attempt to represent the different basins as reservoirs, different parts of the basins as reservoirs. For example, the surface and the subsurface as interlinked reservoirs, not necessarily linear any longer, to build what became known as lump conceptual rainfall runoff models. The pioneering efforts of Lindsley and Crawford with the Stanford watershed model, ultimately leading to the Sacramento model, is representative of this era. Once again, the idea is to add richness to the representation of the basin, but still realistically considering the data as a very limited resource. Since more parameters are involved, calibration is harder in conceptual models. Nevertheless, it's possible. And if you look at the diagram on the rightmost section of the screen, by trying to isolate the response functions in different parts of the basin. For example, using base flow for calibrating subsurface reservoirs. Maybe the most important advance with these models is the explicit acknowledgement that we can use our understanding of different hydrologic phenomena and responses to calibrate models. In other words, understanding the physics matters to overcome data scarcity. Increasingly available computing power, far more than readily available data, started the era of distributed hydrologic models around the mid-1970s, with increasing attention to physically based formulations. Most, like the original MIT catchment model, were hybrid representations of the basin, physically based routing, and conceptual representation of water fluxes. Those models required the segmentation of the basin into interconnected hill slopes that flowed into an interconnected network of channels. In urban settings, dominated by the routing, these models did well. Yet scarcity of data for parameterizing all of the distributed elements was a challenge for calibration. For the most part, data on surface attributes that were input into these models had to be manually obtained from analog sources, like topomaps, which was a painfully time-consuming and expensive exercise. The late 1970s through the 1990s yielded a significant number of physically based distributed hydrologic models of increasing sophistication. Examples like Mike Chi, T. Reeves, HRC, DHM, and their derivatives. Arguably, these models try to represent hydrologic processes like evaporation, infiltration, transpiration, and runoff everywhere over a discretized basin. The goal was to use the best understanding of the fundamental physical processes, commonly represented by differential equations. The impetus behind these models, as the figure shows, is the increased availability of digitized data of topography, of soils, and other surface attributes that allowed direct inference of appropriate parameters. At that point, the data consisted of conversions of existing analog information into digitized data that could be manipulated easily. A most important development was the increasingly available digital elevation models. After all, topography does largely control water movement. And in the United States, there was also NEXRAD, a meteorological radar system that promised quantitative measurements of precipitation at high resolution continuously over the country. In my opinion, the watershed moments that changed the way we think of hydrology and models were the launching of the Tropical Rainfall Measuring Mission, which you can see on the left of the diagram, in 1997, and the Shuttle Radar Topography Mission in year 2000. They provided or promised near global precipitation at resolutions as high as 4 kilometers and global topography at 30 meters resolution. Arguably, the two most fundamental inputs to hydrology were available now everywhere. Data records were not measuring hundreds, but in millions of records. These data sources are augmented with dozens of other satellites from NASA's Earth Observation System initiative, and their successors throughout that have been going up throughout the many years. Now we have observations on vegetation, for example, from the Terra Modis, of groundwater, for example, from the GRACE satellite, surface temperature from several sources, surface roughness, land motions, very high resolution of topography, global rainfall with the Global Precipitation Measuring Mission, and soil moisture with SMAP, SMOS, and Sentinel. Literally thousands of millions of records globally every single day. Naturally, hydrologists immediately adapted the distributed physical models to this era, to this data-rich reality. Finally, the data availability was consistent with the model aspirations. Models like TRIPS, shown in the figure, can quickly download topography at very high resolutions, sometimes down to a meter, and automatically create gridded or triangulated representations of the basin. Precipitation can also be downloaded from a variety of sources. Soil types and parameters are also available. Soil moisture and vegetation can also be obtained. The models were extended to do all sorts of things. In the diagram is the TRIPS output of soil moisture with different resolution representations, where you can then study what is the impact of the discretization. In this diagram, we show TRIPS producing landslides, and you can see the impact of resolution on the total failure area of the landslides. TRIPS also now handles vegetation. New data has in fact allowed us not only to build these models, but have a chance at confirming and verifying the results. Soon, hydrologists and meteorologists realized that the proliferation of data made exercises like linear time assimilation of precipitation and soil moisture possible, which moves us to the next stage in my story. of data assimilation. That leads to forecast improvements, but also, most importantly, to model and process insight. The Weather Research and Forecasting Model, WRF, is a platform of choice to many hydrologists, in part because it is well developed and it's integrated very well to a land surface model, NOAA. This platform and others have been used for the assimilation of precipitation from TRMM, or the Global Precipitation Measurement Mission, and soil moisture from SMAP and SMOP. In the picture, in the diagram, you can see the basic concepts of data assimilation, showing assimilation and prediction in time from WRF, as well as assimilation of soil moisture throughout depth in the soil column. The tools of estimation theory, variation of methods, and various Kalman filter derivatives can be used to process an extraordinary amount of data with the goal of improving model performance, including effectively increasing the resolution of the remote sensing products. It should be mentioned that assimilating and improving the resolution of precipitation and soil moisture are extraordinarily difficult problems. The variability in time and space of the phenomena is very, very large. Ultimately, better models or impossibly large resolution in observations is the solutions. In the meantime, assimilation does provide improvement. For example, in this figure, we see an assimilation of precipitation from a 20-kilometer, 6-hour NCEP stage 4 input, average out to 36 kilometers to represent and mimic the global precipitation measuring results, measured at the continental level. And the idea is then to assimilate the data and produce precipitation of better accuracy and more resolution at a 9-kilometer resolution in a subdomain in the diagram D2. What we can see in the three diagrams is that you see the observations at the top, you see the assimilation experiment at the middle, and you see an open loop run of the WRF model. Clearly, the open loop model diverges with lacunarities of rainfall that do not appear in the observations. And the assimilation does improve. In the parallelogram, you can compare the middle picture and the upper picture and see how the representation has improved significantly, although not perfectly. In this other diagram, it's the same exercise, again, assimilating at very low resolution, 36 kilometers, going down to 9 kilometers in a subdomain. And again, you see how the assimilation in the middle does reproduce and recaptures the observations of precipitation that are shown on the upper diagram. So it is clear that assimilation can indeed improve information, improve the model output, and increase resolution. A very, very hard problem. It can further assimilate, in this case, soil moisture data into the NOAA model, linked to the WRF NOAA system. And in this diagram, what we show again is assimilation at the continental level at a 36 kilometer resolution, going down to 4 kilometers in a subdomain. In the time series shown, you see the latent sensible heat, the sensible heat and the latent heat fluxes. And again, you can observe how in fact the assimilation improves considerably the behavior of the model. Improvement relative to the soil moisture estimates are shown in the table on the right, and what you can see is that the errors measured by root mean square error, mean absolute error, and the correlations do improve considerably in the top part of the soil, but the improvement is not as good as you go deeper into the soil. In this figure, rather than simply assimilating precipitation or soil moisture separately, we assimilate both the precipitation from the TRMM satellite in this case and the soil moisture from SMOS simultaneously over the continental US, looking at improvement in hourly soil moisture in a much smaller domain of 4 kilometers. So going again from 36 kilometers continentally, 6 hours records down to 1 hour, 4 kilometer resolution. The results are compared to assimilation of just precipitation or just soil moisture, as well as to the open loop operation of the model. The combined assimilation improves the results in any one variable only. It improves over the results of assimilating any one variable only. It's certainly true on the surface, but the improvements are marginal at best as we try to improve the soil moisture in deeper parts of the soil column. The use of modern tools of data analysis and machine learning are now feasible options for hydrologists, which brings us to another point in this chronology shown in the figure. A good application is the inference of precipitation on the ground from brightness temperatures measured at different spectral channels or frequencies by passive radiometers in the global precipitation measuring mission and its precursor TRMM. As the figure shows, different radiometric frequencies on the left side of the figure respond differently to rainfall. It is different over the oceans and is different over land. The figure shows the rainfall and the brightness temperature and the different channels or frequencies. The sidebar indicates the dynamic range of the spectral channel in question. The higher the range, the better is the channel in detecting rainfall. It is also clear from that figure that the oceans and the land do not behave the same way. In a true exercise of massive data analysis, Epteha et al. Divided the globe in regions of ocean, land, coast, and inland water bodies, as shown in the upper right figure. And they then paired brightness temperature at all spectral channels from the TRMM radiometer, the 1B11 product, and rainfall at the ground as estimated from the TRMM radar, the 2A25 product, over different parts of the world, creating a massive dictionary of pairs of brightness temperature and rainfall. Given a vector of new measured brightness temperatures, statistically closer neighbors are found in the dictionary. Based on the rainfall detected coincidentally over those neighbors, the algorithm first decides if it is raining or not. If it is raining, it creates a weighted average of the corresponding rainfalls to produce what we call the shrunken locally near embedding algorithm for retrieval of precipitation, or SHARP. SHARP performs extraordinarily well. In this figure, we show the rainfall from TRMM radiometry, the 2A12 product on the left, the TRMM radar, PRA25 on the center, and the SHARP algorithm results. These are instantaneous rainfall estimates from several major tropical storms over several parts of the world, Africa and the United States. First of all, it should be pointed out that they all agree within reason. Do notice that the radiometry, the 2812 product, shows less resolution and shows precipitation over a larger region. Second, notice the increased resolution of the sharp product, although its input is only the measured radiometry, not the high resolution radar. So it increased the resolution significantly. Third, the range of estimated precipitation is different by all products. The next figure highlights how the sharp product reproduces reasonably the distribution of rainfall resulting from the radar measurements over the land and coast. In the bottom part of the figure, we see those distributions. Some differences are clear between radar smart and the estimate of the passive microwave measurements, but they're fairly consistent from what we know. Over the oceans, though, the radiometry product has a distribution that is very much skewed to the very low intensity precipitations. And as seen in the previous figure, as I pointed out before, it spreads over larger area. This is a very well-known behavior. The behavior of sharp at the annual precipitation level is also excellent. In this figure, we show the scatter plot of sharp versus the radar estimate and the radiometry product versus the radar product. Sharp is closer to the radar since it is the learning of the algorithm was directed by the radar product. The color indicates the density of rainfall intensity pairs. Red is higher density. The radiometry product shows a slight bias, low, as we know. It has less intense rainfall estimates and a larger scatter. Most important to the point of this talk, sharp is strictly an empirical approach and processes 4 to 6 terabytes of data every single day. More than 25 million rainfall pairs of radar and radiometry were used for creating the dictionaries. This would have been inconceivable just a few years ago. The Soil Moisture Active Passive Mission, SMAP, launched in 2015 and shown in the slide, promised a revolution in the sampling of a key hydrologic state, one that controls practically all hydrologic fluxes. The mission planned for coincident active and passive measurements with radiometers and radar in the L-band. The idea being to resolve moisture at high resolution with a narrower swath radar and train and merge with the radiometer to obtain a high resolution image, with the goal being combined of 10 or less kilometers. Unfortunately, the radar failed a month into the mission. Since then, the challenge has been to figure out a way to obtain high-resolution results from the low-resolution observations. Significant progress has been made, particularly relying on complementary observations from other satellites like Sentinel and using the month of coincident observations that is available from SMAP. An obvious approach would be to use tools like SHARP or other machine learning techniques. As shown in this figure, the results of using the coincident month of observations of radar and radiometer with MAP and processing the data with a dictionary method like SMART or by using neural networks to produce high-resolution output is not as satisfactory. There is improvement when compared to radar and radiometry observations alone, but it is marginal. Again, compare the last column to the left radiometer output. This is 1% improvement, we would agree, is good but marginal. There could be many reasons for this modest result. One is lack of sufficient coincident data to train the algorithms. The other is that soil moisture is, on the one hand, a continuous smoother variable than rainfall, exhibiting less well-defined edges and hence making it harder to tools like the one we use in SHARP or in neural networks to detect the images. On the other hand, soil moisture is also dominated by different processes during wetting and drying phases. And these are a function of other variables like precipitation, topography, soil type at different times. This latter argument calls for the introduction of more physical intuition and understanding into what are otherwise purely empirical approaches. Epteha and Bras provide an example of such possibility, as shown in the figure. The approach followed a very similar concept to the soil moisture estimation algorithm used by the SMAP mission. The brightness temperature observed by the L-band radiometer as a function of polarization depends on surface and canopy temperatures and parameters as shown in the equation. This is the tau omega model. The parameters are the soil reflectivity, the R sub P, vegetation transmissivity, the gamma, and single scattering albedo, the omega. They in turn depend on soil moisture and vegetation water content. Brightness temperatures and temperature observations can be used to obtain the mentioned parameters, which in turn can be related to soil moisture. In the simplest approach, the single channel algorithm, omega is constant and gamma is obtained from vegetation indices like NDVI. Fixing those two variables allows for the solution for soil reflectivity. This reflectivity and a dielectric constant obtained from the type of soil can then be used in the Fresnel equation to obtain soil moisture. In the spirit of seeking physical guidelines to constrain the statistical analytical solutions, Epteha and Bras constrained the solution space of parameters using readily available information on soils. The algorithm is called the Constrained Multi-Channel Retrieval Algorithm, or CMAC. So, for example, in the figure, using a high-resolution 1 kilometer maps of soil texture, clay fraction, and porosity to optimize the solution of the tau omega model, but this time constrained by a priori ranges for the horizontal and vertical polarization of reflectivities, the first two diagrams of the United States on the lower left, and the range of vegetation transmissivities, the rightmost lower diagram in the picture. These were obtained, as I said, from available digital soil texture, clay fraction, and porosity. These very simple constraints, simply given an a priori range on possible variables, yields amazing results. In this figure, we show the results of a single channel algorithm and the CMAC, the new concept, in estimating soil moisture over the United States, or the continental United States. The important observation is the general fidelity and the much increased resolution of the output if you compare the leftmost diagram and the rightmost diagram. The rightmost being the new algorithm. What you observe is significant further detail on the soil moisture. The resolution, interestingly enough, of the new product now follows the resolution of the constraining input ranges that were provided at the beginning of the processing. So we went from low resolution radiometry to high resolution soil moisture with significant accuracy by simply constraining physically 3 of the parameters of the model in the optimization. In the next figure, we show the same type of results for water content. Again, higher resolution is obtained with the new approach, although it starts from low resolution observations. To confirm and partly verify the result, we compared 2-point observations and land cover types that were collected throughout the United States. Over the United States, remember, grasslands, croplands, and natural vegetation are some of the most common land covers. This scatter plot shows that CMAC seems to be slightly biased relative to the point data, and the single channel algorithm is biased low. It is also clear in the second panel to the right that estimates are shown for every gauge for comparison, that the algorithm overestimates, it turns out, for low soil moisture and underestimates for high soil moisture. Some biases also occur in estimating vegetation water content. We discussed, and it is shown that these biases and errors can be mitigated by fine-tuning the physical constraints given as prior information. Again, the message here is that this is a data and computationally demanding exercise. Each day, the algorithm processes about 0.5 terabytes, and it takes an hour of computation in 20 cores to do a day at 1 kilometer resolution over the United States. The previous illustration points out, though, the value and the need to augment analytical statistical big data approaches with hydrologic knowledge to constrain and guide the results. So basically, we are arguing that to guide the empirical machine learning approaches that we all want to use and should use, we're going to have to constrain them by knowledge of the hydrology and by data like topography, vegetation, soil features that are readily available. Ironically, it seems that history is repeating itself. As we get to this last point of the chronology, the big data processing period, the data is indeed abundant, even overwhelming. The tools are powerful, even amazing, and go a long way in exploiting this new data-rich environment. But at the end, I repeat, but at the end, further progress requires good knowledge of the hydrologic processes and the ability to develop hybrid approaches that bring that knowledge to the new era of big data. Thank you so much.
Rafael, thank you very much for a wonderful presentation. I'm just double checking that I can be heard. Thank you. Very good. Please join me in giving Rafael a round of applause. I know it's virtual. It's the best we can do at this point. We will see you at some point. And I would encourage the audience to please type your questions into the question box, and we will answer those as we go along. So please don't hesitate. And Rafael, I had a question kind of to start with, which is focusing on toward the end of your presentation. Can we turn this around in some ways and use your approaches to optimize where we are measuring on the landscape, where we would put our most, the highest, the most expensive instrumentation, flux towers, et cetera? Is there a way to turn around the uncertainty to help us drive a monitoring network?
Thank you, Scott. Let me just begin by saying I wish I could be in front of all of you, and thank you all personally. But it is amazing what the new technology can do. Your question is very apropos because in many ways that's what Langbein was doing at the end of his career. He was asking the question of where and how should we measure so as to optimize, maximize the information need. I think that nowadays the balance, as I say in the lecture of that Langbein refers to, has changed. So it's not so much an optimization of where to measure and how, because there's so much ability to sample, but it's more an understanding of reducing the variability so you can provide better a priori information to the very powerful tools that we have now. I am convinced that the more we do that, the better the results will be, that the extremely powerful and certainly desirable tools that we see now in machine learning will only carry us so much, and that's been our experience.
Okay, thank you. I'm looking for questions in the question box. I am not seeing others yet, but I'll give people just a little bit of time. This is a new way to have our seminars, so it is a little bit challenging. In the meantime, I'll toss one other question out, which is, when I was a graduate student working on spatial variability, et cetera, this concept of temporal stability came forward from, I think it was Vachaud and Don Nielsen and some others, looking at trying to reduce the number of detailed measurements we might need in the field by looking at where the wet parts of the field are always the wet parts of the field, et cetera, et cetera. Has that gained any traction in these kind of approaches?
In fact, I make a little bit of a reference to that when I was talking about the conceptual models, the era of conceptual models, and it's still applicable here. What many times we fail to realize, I think, is that we look at all the data and all the continuous time and all the processes and try to fit the models to that continuum without realizing that at different times there are different mechanisms and processes operating. Let's take soil moisture, for example. During the wetting phase of soil moisture, clearly the most important thing by far in there is the rainfall itself. The variability of the rainfall will define largely the variability of the soil moisture in space and in time to a large extent, but in space in particular. But during the drying phase, with no rainfall, the processes that are operating of redistribution of moisture are completely different. And hence, I think it behooves us ultimately to think of even this using these empirical tools by segregating processes and using empirical tools during when some type of processes are operating and others and develop different models when other types of processes are operating. And rather than trying to lump it all together, I don't think that machine learning or any of these tools are really truly going to be able to respond and encompass all those different processes. And in fact, it's unnecessary. You're stressing the tool more than you have to, knowing that in fact different mechanisms are in action, these different regimes are in action.
Thank you, Rafael. We have a few questions now, once I figured out how to use the question box. Apologies. This question comes from Graham Fogg. Graham, thanks for your engaging lecture. Better coupling of groundwater and surface water remains a major challenge, in part due to the errors in evapotranspiration and precipitation, often exceeding the magnitude of groundwater recharge. Can you comment on a path forward for dealing with this challenge?
Yeah, interesting question. I couldn't agree more. It turns out that one of my colleagues working with me here at Georgia Tech and I, under the SMAP mission, have been looking at the possibility of using SMAP soil moisture, which measures just the upper layer of soil moisture, to try to detect when there's shallow water, shallow groundwater, whether it's purged or whatever, but shallow. Because during shallow groundwater situations, there's exfiltration, and what we're observing is that the variability at the surface of the soil moisture measured by SMAP reduces considerably when the shallow groundwater is in action, as you would expect. So using it, we believe that, and in fact have done some studies about it, that we can indeed detect globally using SMAP when there's shallow groundwater. You say, well, if you know the shallow groundwater, what is the value of that? Well, the value is that to initialize modeling, for example, globally, of land surface models, for that, it is terribly important. Even if you just know that it's shallow or deep, that will improve your results considerably. If you can narrow that knowledge to how deep or how shallow, that's even better. But just a statement, or is it in the top 1 meter or deeper, will make a big difference. And I think we can do that.
Great. Thank you. The next question comes from Ana Barros. Rafael, thank you so much for a tour de force. What is your insight into the balance between predictability that requires fundamental knowledge and the need for effective predictions?
That's the dilemma, Anna, that we all face. I think, like all empirical tools, at the end of the game, only know what they see, what you give them. And sometimes it's not obvious to you, but you're giving it to the tool somehow. The ability to go beyond that ability to generalize either space and time to predict will continuously demand better understanding of the phenomena that are ongoing. Now, the gap is certainly narrowing. I think the tools are so powerful, and as the subject of the talk is all about, the amount of data is so large, it's so big, that these tools can in fact see a lot of phenomena. So in the past, our observations were very limited, and we were seeing a very narrow spectrum of the, let's say, the dynamic range, and hence that's all we could do. And to go beyond that, you had to extrapolate with knowledge significantly. Now that range is a lot broader, and hence we have a better chance of capturing what the future might bring. but there's always a limit to that. You never see it all. So I think that physical knowledge and intuition is still very important.
Okay, thank you. Our next question comes from Catarina Matos. Thank you for your presentation. In your opinion, with all the data available, is it becoming increasingly more difficult or easier to evaluate our model outputs?
I'm an optimist. It's becoming easier. It is. Let me rephrase that. It is becoming possible, which before wasn't really, in some way. So easier is all, it's a matter of taste. At least it's possible. So I welcome the amount of data. I think we just have to be wise on how we use it, and there's no doubt that it's allowing us to do things that were never dreamt of. Again, Langbein, a real giant in his time, would this would be inconceivable to him to see what we're doing now. Frankly, when I look even in my career, 40 years doing this, it's completely inconceivable. That we would be doing what we're to think that we would be doing now what we're doing. If I had thought of it 40 years ago, I used to give another talk which is a tongue-in-cheek title, "Everything I Learned Wrong at MIT," and it was partly addressing how much we have learned and how far we have gone.
Okay, thank you. All right, we have some questions in the chat box. I'm going back and forth, and so let me see if I can. This is from Beiling Lee. Hydrologic processes are related. Surface soil moisture may be affected by root zone wetness, which is not observable. How do you take that into consideration in machine learning?
That's the challenge, because so far, again, the machine learning and tools like that can only tell you what you give them. It can just interpret what you provide. Now, there are ways to indirectly observe that, or try to. Observability gets limited quickly, but you can. For example, the vegetation moisture content is a measure of the health of the plant, and is certainly a measure of the water in the root zone. So there have been attempts to use some of that to infer those conditions. What I was saying before about using vegetation water content measurements as well as soil surface measurement to get a sense of shallow groundwater that impacts the root zone moisture, I think that is possible. And it's inferred simply by looking at the behavior of the soil moisture. How would it behave if you have a root zone that is very wet or a root zone that is dry? And I think that behavior at the surface changes, and you can see that. So it's an indirect observation until we get better, but I think we can learn something.
Okay, thank you. This is a question from Siren Harman. The concepts of regularization and sparsity, that underlie the dictionary learning methods you've used have incredible powerful in statistical learning. Do you think these methods are underutilized in hydrology still, and are we behind the curve?
I think they're underutilized still, and there's still a lot more to do with this. And frankly, this is an area there where the cross-pollination of fields is absolutely necessary. And many of you younger people coming along have an incredible opportunity to do that. You're right on target. The work I presented on this by Ebteha, who was my postdoc, for a while, is extraordinarily powerful, and there's no question that his knowledge of of these tools opened my eyes to a whole field that I did not know anything about. But that's the beauty of being a professor.
Okay. Well, I'm going to follow that question with from Jeff McDonald, which I think is an appropriate question. Jeff says, and great talk. What advice would you give to early career researchers starting out today on what you've seen in the field in the past 40 years? And your perspective from as an administrative leader. What is different for an early career person now versus when you started? And what 3 things would you say are the most important for them to follow a successful path? Very easy question, Jeff. Thank you.
Well, yeah, three-part question, Jeff. I'm getting old. I'm not sure I can remember them all, but let me let me begin with from the end going back. To be very honest, these days the good and the bad thing is that in hydrology, we went from a period where there were very few of us, late 60s, early 70s to the 80s, to an explosion of need and importance and value given to hydrology, and hence the corresponding increase on bright minds going into the field. So that's the good part. The bad part is the competition is fierce, and hence that's just a reality of it. Related to the first part of your question, I have 2 things, Jeff, that I would give the younger among us is one, follow your instincts, uh, and do whatever and whenever you're happy doing whatever you're doing. Don't compromise in that sense of satisfaction, personal satisfaction and happiness. You have to stick to that. Don't do something that you don't want to do because somebody else says so. The other part of it that has been very powerful for me from early on, since I did my PhD, which was on estimation theory, more electrical engineering than hydrology, is the ability to scan the horizon of the sciences, uh, to look across and be able to make the interconnections and connections that are so important uh, to make progress. I am convinced that creativity is part invention from nothing. Let's put it that way, if I can put it that way. But a lot of it is the ability to make connections, to see how a process and an approach, a thinking that is carried out in business is applicable to hydrology. I'm picking that on purpose, and in fact, I think there are examples of that. Uh, but that ability to make the connections, to join, be able to have a broad enough mind to 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 learn from what others are doing, even if they're not in your field, to be well read, to be curious, that is absolutely necessary to survive in this day and age.
Okay, thank you, Rafael. I think might have been one more piece of that question, but I think we'll save that for when we can have a beverage all together. This is a question from Remco Aulenhout. Thanks, Rafael. Comparing gaining hydrologic process understanding in the data-rich to the data-poor era, are we still asking ourselves the same hydrologic questions as before? Or can and should we ask new questions that we didn't even dare to ask before? And if yes, what questions? Kind of leads on from answering Jeff's question. Where do we go next?
Yeah, I in fact believe that we have been asking new questions. hydrology has moved, and I made reference to something Pete Eagleson and I wrote an editorial opinion piece from a field that was focused on what then was called engineering hydrology, small scale problem solving focus, to really and truly thinking broadly at continental levels. The issue of land fluxes, global hydrology, the relationship of climate to the land masses, all that may not sound new to some of you, but it sure was new to me. And it required complete relearning and refocusing of the hydrology I had learned in class. So I think we're constantly evolving this way, and if you go back at the career of many of us, you'll see that what we do now has nothing to do with what we're doing now. I had a professor at the end of my undergraduate years, that made the statement that the land masses were absolutely irrelevant to climate. And you can see why. The oceans indeed are massive system that provides a lot of the inertia of the climate and dominates a lot of the Earth. But since then, we realized that if you just assume that the Earth is a great ocean, you're going to be wrong. And besides, not many people live in the middle of the ocean. But that was the belief then. So you can see the change, the sea change, to make a pun in that of what has happened. Where is it going? Well, I do believe that the integration of the hydrology with the biosphere is crucial. We have done a lot of progress with vegetation, and we're still just hitting the tip of the iceberg on that. But there's a whole biosphere of microorganisms that impact the hydrology that we still don't know how to deal with. So to me, that would be an exciting future. In a twist of fate also, and given the needs of the world, I also believe that something I worked back in the 1980s, which was the tools of hydrology and the knowledge of hydrology in food production, in agriculture, and many ideas that back in 1980 were there, but impossible to put into effect. And I go back and think of some of the things we did in 1980. Some of my students did great ideas, but they remain and stayed on paper because there was no way of carrying them out. Now it is possible to do that, and the sky is the limit on that, as far as I'm concerned.
Okay, thank you for those insights. Well, I think we will begin to wrap it up. Rafael, I'm not sure if you're able to see in the chat box, but the list of great talks, thank yous, etc., from the audience is about a kilometer long in the chat. And I'll just summarize. I think Steve Burgess says it very well. This is from Steve. Walter Langbein would have appreciated your comprehensiveness and integrative scholarship in showing what is possible to move hydrologic science and practice forward. Thank you for your time and effort preparing and presenting this excellent lecture. And I think that sums up what a great lecture this was. Thank you, Rafael. Thank you to the audience.
Thank you so much, all of you, again. I just hope to see you all soon, certainly next year.
Yes, we will all be there. Thank you, Rafael. And I want to also just give a shout out to all of the awardees that gave presentations, to Rafael, and also when we get to the Witherspoon lecture. This has been a challenging process to put all this together. I really appreciate the patience and energy that all of our speakers and awardees and citationists have put forward to make this happen. I appreciate the audience who's got great questions. There's still a few questions we didn't get to, but we will afterwards. And I think we will begin to wrap it up. I have a couple of just very quick announcements for the rest of the team. Just remember, our hydrology section business meeting is indeed today at 1800 Eastern Standard Time. And interestingly, if you go looking for it in the program, and if you search by section, you will not find it. So please search by day. So you come down to Tuesday and come down to whatever time zone is equivalent for 1800 Eastern Standard Time for you, and you will see the hydrology section business meeting. And we'll have bring a beverage, as we often do to these, and you'll hear from updates on what the section is up to. Secondly, please consider signing up to be an OSPA judge. We have some really tremendous presentations so far. I've been judging yesterday, and the kids, everybody really deserves this. So please, our students are counting on you. Please sign up. Just judge a couple. That would be really great, and they're really quite good. The next thing is we are holding these section meet and greets. So these are just very informal Zoom meetings at around the dinner hour East Coast time, and you'll get a chance to meet some of your hydrology section volunteers. So that begins, we had our first one with the students on Monday. It will recommence on Thursday, Friday, Monday, and Tuesday of next week. And just to let you know how to get there, that too is a little challenging with the app, is come into the section and come into the lobby, the meeting lobby, go down on the right-hand side to networking, go into that screen, go to pods, P-O-D, and go to pod number 1, and you click there and you'll find a Zoom link that will take you outside of the meeting, and then you'll actually be live with our executive committee or with WRR, whoever's up on that day. And let's see, lastly, our award ceremony. The union award ceremony is indeed tomorrow, as I said in the opening, Wednesday, 1800 Eastern Standard Time. So you'll see our hydrology award winners from the union level there. And then finally, I just want to remind you that the hydrology section Paul Witherspoon lecture is on Thursday, December 10th, same time as the Langbein lectures was today, 1330 Eastern Standard Time. And that will be presented by Giuliano Di Baldassare on the hydrologic extremes in human society. So please join us for that. And we will also be awarding our early career award winners at that point. Okay, I think without further ado, again, please join me in giving our 2020 Langbein Lecture appreciation and award and applause. And Raphael, thank you so much for a wonderful talk. That concludes our Langbein Lecture for today. Enjoy, and I will see you at the business meeting, I hope all. Thank you.